Hi, NA Physics. Let's talk today about beats. Before we do, why did the people dance to the vegetable band? I'll tell you at the end of the video. So I found this really cool simulation from our friends at physicsclassroom.com. And look what it is. They have a tuning fork, a simple instrument, mounted in a tuning board, a lightweight wooden box that can trap some air and make the air vibrate at the same frequency and so amplify the sound. And now you can make the tuning fork vibrate at whatever frequency you'd like. See that little doodad that they have right there? That's going to be a weight that you can move up and down, and you can vary the amount of vibration per second. So you can see as I change this frequency, that little dooder is moving up and down. So if I tap the thing, now you can't hear it, but you can see the longitudinal waves going out. And so you can also see this really nice graph of pressure versus time. And you're not surprised at this. This is 100 hertz. That means it's going up and down 100 times every second. And so you can see that that's what the pressure does. The pressure is going to do one complete higher pressure, lower pressure cycle and come back and be ready to start again at 100 times a second, or in 100th of a second that happens. Okay, now I'm going to turn that one off. Now this one over here, I can I'm going to set it at 100 hertz as well and get it started. But now I'm going to go ahead and adjust the weight as it's vibrating, and look what's happening, everyone. Look how the vibration is now happening quicker, 105 hertz. So 105 times per second. So if you look here, you see that no, it's not doing a cycle in 100th of a second. Rather, it's doing a cycle in less than 100th of a second, because it's got to get those extra 5 in there in the second. So it has to be a little bit quicker. And so now, if I took those and I played them simultaneously, now you can't hear this, but you can see it very well. What would you see? Well, at first, you would see that they're fairly in phase. Like in this first one, they're fairly in phase, and here they're fairly in phase, and so you're getting this large interference pattern. But what you can see that as we go over to the right, they get less and less in phase, and you see this first interference pattern is going to be pretty tall, pretty big amplitude, and then a little less and a little less, and it's hard to see only over 0.03 seconds. But if I zoom this way out, you can see that since they're getting a little bit less and less in phase and a little bit more and more out of phase, that amplitude is getting smaller and smaller, and you can see that I don't have as great of an example of constructive interference. In fact, I'm going towards destructive interference. And by the time you get out pretty far, you can see that you have complete destructive interference there at 1/10 of a second. 1/10 of a second. Should I have saw that coming? Yeah, I should have, and you'll be able to too. And you can see that it's going to continue to fluctuate like that, getting in phase and getting out of phase, and getting in phase and getting out of phase. Now you understand that a little bit if you did the prep videos and you saw the mini lesson and so forth. But even if you didn't, it does make a lot of sense that because those frequencies are close but not exactly the same, they're going to continue to fluctuate between in phase and give you constructive interference, and out of phase and give you destructive interference. That idea is called beats. Beats is this sound that when two sound waves are with slightly different frequencies are simultaneously played, and because they have slightly different frequencies, you get this constructive and then destructive alternating pattern. You can see it here too. So if I had a sound that was 100 hertz and I had a sound that was 120 hertz, that I'm going to get that sometimes they're going to be pretty much right in phase, like over here, and then they're going to be times where they're going to be pretty much right out of phase, like over here. And notice something, please, that these two are 20 hertz different. So if I said to you, how different are these? You'd say, okay, well, the difference there is 20 hertz. I know you might be going top to bottom and negative. Let's ignore the negative. And so do you notice something here, that from the time that they're in phase till the time that they're in phase again, is 0.05. Think about that. That's a 20th of a second. And so we can see that the 20 hertz difference in frequency and the 20th of a second seem to relate to each other, and they really do. So because of that, we're going to get them to go constructive and destructive 20 times a second on that last one. And over here, you see something. We have a tuning fork that's vibrating at 440 hertz, and we have another one with a little piece of putty on there that's more difficult, so it vibrates a little slower, only 438 hertz. And so that means that this wavelength is going to be a little bit longer because this wavelength is a little bit smaller, and this wavelength is going to be a little bit smaller because this frequency is a little bit bigger. Those two products will be the same, but regardless, the frequencies, they are not the same. And so you can see that they are going to continue to go in phase and out of phase. Times where we have compressions lining up and rarefactions lining up, it's going to sound loud. And places where we have compression and rarefaction lining up with each other, it's going to sound soft. So it's going to continue to alternate between loud and soft. Now, calculating the beat frequency is super, super easy. And that's actually what I calculated before when I did that subtraction. We say that the beat frequency is just the difference between the two frequencies. Now, I don't know which one is going to be bigger and which way you're going to subtract, so we generally write that with absolute value signs around there. So what would be the beat frequency here? Easy one, 440 minus 438, 2 hertz. So 2 times a second, it's going to go loud and soft and loud and soft. One quick example before we're done here for today, and I have a little tie-in with Doppler effect and beat frequency, because just beat frequency itself is pretty easy. So here I have 2 identical car horns, and they each have a frequency of 395 hertz. One of the cars is moving at an observer with a speed of 12 meters a second, and the other car is parked. Now, the speed of the sound is 343, like we often see that it is. What's the beat frequency heard by the bystander? So what this involves, the last step is going to be to say, well, the beat frequency is going to be the difference between the two. Now, this moving car it's moving at the observer, so we know that the frequency that you observe is going to be higher than it should. That's right. And so it's going to be something minus the 395 hertz, and that's going to be the answer here. Now, what you have to do is you have to decide, what is that Doppler shifted frequency? What is that higher frequency that goes right here? Why don't you pause the video for a second and figure that out. Okay, so I hope while the video was paused, you said that the observed frequency is the source frequency times the fraction that tells you what percentage. And when you're moving toward, when you have a moving source moving toward an observer, it's 1 minus velocity of source over velocity of sound, like this. If you go ahead and put in the 395 hertz here, and you put in 1 minus 1 over the 12 for the velocity of the source, divided by the 343 for the velocity of the sound. Be careful of those subscripts. You're going to see that this comes out to 103% of the original frequency, which is 409.3 hertz. That's what I'm going to put in right here, and when I subtract those two, I'm going to end up with 14 hertz. Hey, last thing before we go, why'd the people dance to the Vegetable Band? Hey, they had a good beat.